recently went to Mammoth for the weekend and was on the way back with a couple friends when the subject of inorganic chemistry came up, and I realized how little I knew about the subject. Specifically, I didn't really know anything about how inorganic synthesis works. I know quite a bit about organic synthetic chemistry from the classes I took at UCSD in undergrad as lectures and laboratory classes, but I also had some experience working with synthetic organic chemists in my research at UT Austin, because a lot of the molecules that we use as substrates for enzymes that I studied were made synthetically because they're either hard to isolate naturally or they aren't natural substrates. Inorganic compounds are compounds that don't contain carbon. And this is a very, very broad category. But you can also say that organic chemistry is a very broad category because of the chemical space that is allowed by the carbon atom, because it can readily bond with oxygen, nitrogen, hydrogen, using single, double, and triple bonds. It's able to use all of its valence electrons to bond to other atoms. And the rest of the periodic table is less fortunate in its abilities to form complex molecules, but it still is an enormous chemical space. Most of my current work and previous work deals with organic chem, so I wanted to do an episode on inorganic chemistry to boost my awareness of this far-reaching realm. I answered my question about the process of the synthesis of organic compounds. I found out that if the compound is soluble, it's produced very similarly to organic methods. This involves mixing reactants, usually in a round bottom flask, and letting it incubate at a certain temperature for amount of time. While this is happening, you can monitor the reaction using TLC, thin layer chromatography, or another type of analysis like HPLC, which is another type of chromatography. This is often followed by purification using silica in a column. So this reaction is loaded on the top of the column, and then a particular solvent is used as an eluent, and it is passed through the column using, sometimes with pressure, and this separates the reactants and any products that formed. Since metals can often be oxidized very easily with oxygen, sometimes care has to be taken to prevent this. When I worked with an iron sulfur protein in Texas, I used a glove box that separated the oxygen in our atmosphere from the protein I was working with. And I was able to reconstitute a 4-iron, 4-sulfur cluster in a protein under anaerobic conditions and show activity of the enzyme, which was involved in an antibiotic synthesis pathway in a bacterium. Inorganic metals can do pretty interesting things with their d orbitals. Metals can form quadruple bonds, which consist of 1 sigma bond, 2 pi bonds, and 1 delta bond. Solid metals are held together by metallic bonding. This means that as the nuclei are fixed in space, the electrons are delocalized across the entire metal. Overall, the atoms are electron deficient, but this sharing of electrons allows for conductivity, where electrons are allowed to flow freely when a voltage potential is applied to the metal. The sharing of electrons also allows for malleability, which allows for metals to be molded and altered like a blacksmith was known to do. Another important property of transition metals is that when metals lose electrons to form positive ions like they typically do, they lose their outermost s orbital electrons before they lose their d electrons. This goes against the Aufbau principle, where the lowest energy orbitals are filled, and typically 4s is calculated to be lower energy than 3d. But in that first row of transition metals, you see that the 4s electrons are lost first. This probably doesn't discredit the Aufbau principle, but I think that the ordering of orbitals according to their energy is not correctly predicted by the method of ordering orbitals that I learned. As elements lose their electrons, they access a higher oxidation state. When this happens, they become good oxidizing agents and are reduced, like the permanganate ion, which is in a +7 oxidation state. So now I'm going to devote the whole rest of this podcast to coordination compounds. Coordination compounds formally donate electrons from a ligand. Ligands can be ions, or they can be neutral. For example, look at this palladium coordination complex. There's some differences in convention between organic and inorganic, but you can see that the ligand can have a charge and the overall complex can have a charge as well. And it is the ligand that donates its lone pair to form a bond. But as we'll see, there's also bonding that occurs with the electrons that were initially confined to the metal. Coordination complexes usually are formed with metals in row 3 through 13, which are mostly transition metals, except for 13. From a certain perspective, all compounds are coordination compounds, because covalent bonds are a sharing of electrons in the formation of a molecular orbital. But before they come together, those electrons sometimes belong to one of the atoms and not the other. In that way, coordination chemistry is similar to organic chemistry. Coordination complexes can form in solution from the ligands that are available in that solution. There can be formation of a complex, or there can be substitution of a complex. Often the strength of a ligand is determined by the exchange of that ligand with water. When a metal and a ligand come together to form a coordination complex, the stability of that complex can be measured empirically and summarized in a constant, Kf. A chelated metal is a term you may have heard in the vitamin and supplement context. Chelation means that a metal is coordinated more than once by the same molecule. So the ligand forms a ring with the central metal. One good example of this is EDTA. It's very common in research labs because it will bind many different metals, including magnesium, which is very useful in stopping an enzyme catalyzed reaction that depends on that metal. You might notice that EDTA is chiral, meaning that it has a non-superimposable mirror image. Many other coordination compounds are chiral as well, and they don't have to be chelating ligands. Ligand. I just realized that I was mispronouncing the word ligand. The coordination number in a coordination complex is the number of ligands that are attached to that metal. The most common coordination number is 6, which is an octahedral complex, or a square bipyramidal geometry. Now, this geometry can be analyzed in crystal field theory, which is a theory that assumes that the bonds in a coordination complex are ionic, and each ligand is just a point in space. Since they are ionic bonds between the lone pair and the metal, we don't even consider the electrons in that bond. We consider the electrons that are in the metal itself, and usually it's a positively charged cation. There are 5 different d orbitals that the central metal has, and 3 of them are oriented between the ligands in an octahedral geometry. Then there are 2 that are oriented towards the ligand. Because these orbitals are closer to the electron-rich ligands that are donating their lone pairs, these orbitals are higher in energy. Normally, a metal that does not have any coordination has 5 orbitals that are at the same energy level, and each orbital gets filled with a single electron before an orbital gets filled with 2 electrons. And this is Hund's rule. But when we have ligands, the 5 orbitals are split, where 2 of the orbitals have higher energy, the e orbitals, and 3 of the orbitals have lower energy, the t orbitals. Electrons in that lower orbital can get excited by light and get promoted to the upper orbital. And this absorption gives the color in that coordination complex. And it's interesting, these ligands have different strengths when they are coordinated to the central metal atom. There are weak field ligands and there are strong field ligands. Strong fields ligands have strong pi bonds, which stabilizes the t orbitals and brings them down, increasing the splitting of energies between the t and the e orbitals. These ligands include cyanide, anion, carbon monoxide, nitrite, and amine. The weak field ligands destabilize the t orbitals, bringing the t and e orbitals closer together and decreasing the orbital splitting. Examples of weak field ions are hydroxide, fluoride, chloride, bromide, and water. Strong field complexes, since they have a larger orbital split, they typically absorb a shorter wavelength of higher energy, whereas the weak field ligands, the electrons need less energy to get promoted, so they absorb longer wavelengths that are lower energy. While researching this week, I learned that a complementary color is actually the color that is observed when its complement is absorbed. I thought that was so profound, and I'd never heard that before. But if you think about it a little bit, it can't be a concrete rule, because if you just absorbed a very small range of wavelength, the reflected light is going to pretty much match what is emitted from the light source. But if the absorbed range is large enough, the idea is that you would see the complement. How those ranges of wavelengths are picked, I do not know, but it seems to be a little bit subjective. So I just covered D to D transitions. So this is transitions of electrons within the metal that crystal field theory has located in the metal. But there's also something called a charge transfer. This is when an electron from a ligand gets excited to an orbital that belongs to the metal, or vice versa, where an electron in the metal gets excited to an orbital that belongs to the ligand. And this transition is usually a huge gap in energy and corresponds to an absorbed photon of very high energy, which often leads to a color that is towards the red end of the spectrum. One example of a charge transfer is in permanganate, which I referred to earlier, where the magnesium ion has a +7 charge. A coordination complex with the max number of unpaired spins is called a high spin complex. This is expected for weak field ligands that have a lower level of orbital splitting. A complex with the minimum number of unpaired spins is called a low spin complex. And this is common with strong field ligands, where the energy between the T and the E orbital is large. So the electrons prefer to stay at that lower energy instead of jump up to the higher energy E orbitals. Many D orbitals have unpaired electrons and are therefore paramagnetic, which means that they're attracted to a magnetic field. High spin complexes are more strongly paramagnetic because there are more orbitals occupied by a single electron. The spin of neighboring atoms is random, so paramagnetism is usually weak. However, you can align the spin of paramagnetic complexes when you apply an external magnetic field. This is used to create permanent magnets. The second most common coordination number is 4, and complexes of this number can form tetrahedral or square planar geometries. Tetrahedral geometries are almost always high spin because the splitting is very small. You can also find coordination number 5, like this osmium complex. This is trigonal bipyramidal. Linear complexes have a coordination number of 2, such as this silver amine complex. When carbon is bound directly to a metal, this is an organic metallic compound, and this is a full-on field of research that I won't get into. So ligand field theory is very similar to crystal field theory, except that it incorporates the lone pairs on the ligands to form molecular orbitals. Ligand field theory assumes a covalent bond, so the electrons of the ligand are considered. The lone pairs of the ligands in an octahedral complex form the lowest 6 electrons in the molecular orbital. These are the bonding orbitals. The electrons in the metal fill the non-bonding orbitals, similar to the T and the E orbitals in crystal field theory. Also, there are antibonding orbitals that are very high energy that can be filled when electrons are excited. Today we went over basic concepts in inorganic chemistry, including coordination complex. Major props for getting through this. Thanks for listening.